Broken in two parts unless I crossed out the logarithmic piece. So the goal of the day is to learn how to solve exponential equations, which isn't hard if you'll stay awake. Tyler, really not. We have a theorem up here. Jace has actually mentioned this one in class and got it right. If b is a positive number other than 1, so this is anything other than 1, and you have some b to the x equals some b to the y, it's kind of a common sense thing. So they look the same, x and y have to be the same. It's just a common sense approach. That's how we solve exponential equations. So our first example up here is an easy one. If 3 to the x is 3 to the 7th, Andrew, what must x be? 7. Because visually it looked the same, right? X has to be 7. It's just a visual approach to things. It's the simple stuff. Look at it. It'd be nice if all of them were that easy, wouldn't it? They're not. But the goal is to make them look the same, at least make the bases look the same. If you get the bases to be the same, the rest of it's easy. So we're through slide 1 of 4. Quarter done. There would be MJ.
Watch it not.
It's not. Oh, I made this one.
Oh, yeah, yes, I'm testing security. Now, to solve exponential equations properly, you're going to have to be in the right frame of mind. Like, you're going to have to look at numbers and be able to rewrite them as powers. Like, you should know without a whole lot of hesitation what 8 is a power of. What is 8 a power of? 2. 8 is 2 to what power? Cube. 2 cubed. How about 9? What's 9 a power of? 3 squared, right? And by the way, you can also be thinking about them as themselves to the first one. Don't forget about that understood exponent. Don't ever forget about that understood exponent. Right? Already in your desk. You're right. It'll work. You've been here for the problems I have with y'all being late. Yeah. Way back at the end of the year. What's 64 about? It's power of 8. A whole lot more than that, though. 8 squared, it's 4 cubed. Anything else? 64 to the first, the obvious one. Never forget about the 7. There's another one. 2 something. 2 something. Not 2 to the 4. 2 to the 4 is 16. 6. 2 to 6. And you also got to be thinking about how you can work with fractions. Like another way of writing 1/2. 1/2 is literally 1 over 2, isn't it? What's that understood exponent on that 2 down low? 1. How can you rewrite that?
2 to the negative 1.
2 to the negative first. You got to be thinking about stuff like that. How about a quarter? How can we write a quarter?
4 to the negative 1.
You could write it as 4 to the negative first. It's definitely 4 to the negative first.
Could it also be 2 to the negative 2nd?
It's also 2 to the negative second. Because when you look at 1 over 4, you know, a kid who's pretty good at math will also see like 1 over 2 squared. We'll see that. It's just right there in our head. And those are the kind of things you have to be doing in your head to do this kind of stuff. It's not that bad. So here's our first one. So 4 to the x equals 1/2 raised to the x minus 3. Now you need to seek a common base. That theorem on the front page of your notes talks about b to the x equals b to y. The bases have to be what? The same. The only way that theorem works is the bases are identical. So you look at your bases. You've got a 4 on the left and a 1/2 on the right. What's a common base? Nope. 2. That's kind of the idea here. We're going to seek a common base. Actually, you could use 4. You'd have to raise, this one could be written as 4 to the negative 1/2 power. You could use a 4, no doubt about it. And the common base here is 2. Well, to create a 4 from a 2, what do you do with it? What do you do with 2? You square it, don't you? This is a 2 squared still raised to the x. That's all it is. 2 squared raised to the x. We already talked about rewriting a half. How do you rewrite a half? So we change the exponent to a -1, and we still have this x minus 3 attached right there. Now we did everything. We have common bases. Once the bases are the same, what do we do with the exponential space? Make them the same. We set them equal to each other. It's really a simple property. So we would have 2x equals a -1 times an x minus a 3. And it's distributive property. X is on one side, numbers on the other. It's not too bad. What's that -1 times x minus 3? Get off your phone, bro.
Negative x plus 3.
X plus 3. I know you guys have withdrawals from 4 hours and no funds. Not really. No, I mean, I got withdrawals. Anyways, if you add 2x to 2x, you got 3x, right? You got 3x is 3, what's your x value? Oh, simple equation. And that's probably about as easy as they get. I'm sure they get a little bit harder on the next page. We'll see. But we're halfway down with your notes. So 2 more examples. We have 81 raised to the power of 3 minus x. It's equal to 1/9 of raised to the power of 5x minus 6. And just think to yourself for a few seconds what the common base would be. Think to yourself for a few seconds. Both of those are power. There's actually 2 different choices for common base on this one. I'm just going to use your calculator. How do you know the common base? 9. A lot of times, not all the time, but most of the time, maybe 3 out of 4 times, the fraction usually gives you the hint. Like, to make it 81, what do you do with 9? You square it. And then everything will be in terms of 9. You just got to fix the fraction, you'll be in business. So we turn that 81 into 9 squared. And, the first example I did, I just kind of threw x next to it. Well, the second example I did, what I do with the existing exponent. I wrap it. We have a property that says that I can multiply exponents together when they're written like that. We have a property like that. We talked about it before Christmas. No, we talked about it. But I'm actually using this property, x to the a raised to the b is x to the ab. That's the property I'm using to handle this stuff. So I changed it to 9 squared, and I already had that 3 minus x there, so it stays up top. The exponential space is done through multiplication. I need to rewrite your 1/9. Andrew, how do you rewrite 1/9? Your base has got to become 9, doesn't it? 9 to the negative first power. And wrap the existing exponent. And you can distribute here if you want, or you can do it on the next line, nobody cares. But what are you going to do with 2 times 3 minus x and -1 times 5x minus 6?
Turn them into 6. Or set them equal.
Yeah, you can set them equal, distribute. Might be easier for some people to just go ahead and do the initial step. Set them equal. I'm going to invoke that distributive property since we've been talking about since probably ready to that and work on numbers on them. So if you distribute the 2, what do you got?
6 minus 2.
Minus 2x. Nick, are you with me right now? No, you're not. Distribute that -1, what have you got?
Negative 5x plus 6.
5x plus 6.
X equals
X is 0. That's right. I would shift my x's to the left. I'd make it 3x. On the right, you have 6 minus 6, which is 0. And there are kids who just say this has no answer, but you're not thinking about this through. If you take that 0 and divide it by 3, what do you still have? 0.
And that makes it 1.
What's that?
That makes it 1 equals 1.
Yeah, it does make it 1 equal 1. I think it does on this one. No, it doesn't make it 1 equal 1. It makes it say that 81 to the third is equal to 1/9 to the -6 power. is. Now, look at example B. Your bases are 100 and 1,000. The deal is seek a common base. That's 10. Quite simply 10. So I'm going to write this out for you, and then I'll let you guys do the rest of it. We have a 10 raised to 2, and parentheses attach that to is a 7x plus a 1. There we go. That would have to equal, how do you create 1,000 from a 10? Cube it. And you guys take it from there. Shouldn't take you more than 30 seconds of your life. I think you get a fraction. Yeah, 5x equals 1, 2, 3, 9. Hey, Johnny, you finished with it already? 2 times 7x plus 1 equals 3 times 3x minus 2. Set the exponents equal to each other. Nick, you stuck? You stuck? Nolan, what'd you come up with? Is it -8? It is -8.
Is it?
I think.
No, I don't know.
I feel like it's at -8. Let's see what happens. So what is twice a 7x plus a 1?
14 plus 2.
It's a 14x plus a 2. It's 3 times a 3x minus 2. X minus 6. I don't see anything wrong with it yet. We can do it 9x. Subtract it from 14x. What are you going to get? 5x. We can do that too. Right over there. That'll give you -8. Remember, you counteract addition with subtraction, kids. You're too old to be making that mistake anymore in your life. And the opposite of multiplication would be addition. So, Kendall was wrong. Nolan was right.
Kendall probably exerted himself more on the math though without a calculator.
Nolan was right. Nolan was wrong.
Well, then Nolan's
Nolan doesn't have a calculator. Just accept it. Every once in a while, Nolan has to get a win. He has to. Alright, sometimes it's possible to take two exponential functions down to a common base. In this case, we isolate the exponential function and convert it to a logarithm, and then we let technology, which I'm missing the H on that thing, take over. Now, you have to realize when this applies and when it doesn't, and it always actually applies. Everything we've actually done can be solved with a logarithm. I'll probably make something else up and we can do it with a logarithm. But solve 7 to the x equals 15. Do 7 and 15 have a common base? No, they don't have a common base at all. So this is when we use the conversion to a logarithm. Now, I'll probably show a couple more examples in your notes on this. We're going to use initially, we're going to use log as base. A logarithm of base b, argument a equal to something called e, is equivalent to what? What's it equivalent to? B raised to the e equal to n. Hey, you know, all the kids who can't do basic trig, it's because they can't spell SOHCAHTOA. The kids who can't do basic trig can't spell SOHCAHTOA. S-O-H-C-A-H-T-O-A.
Are you serious?
Yes. Anyways, it's the same thing here. If you can't memorize these conversions, you can't handle these equations. So we've got a simple one in front of us. It's 7 to the x equals 15. We're going to convert it to a logarithm. What's its base? What's the base of the function you're given?
7.
7. So what's the base of the logarithm? 7. Base stays a base. Remember, this goes base, exponent, answer. Kind of substituting in from left to right here. What's the argument of this logarithm going to be? 15. What's that equal? X. Now you can let technology take over. Can you type log base 715 in your calculator? At least have I shown you how to do that yet?
No.
No, I have not shown you how. I've shown you how to change the base. That's why you're nodding your head. Oh,
Yeah.
if you press the log button on a calculator, you don't get an option in the base, do you? So you've got to use what's called change base formula. So here's the other thing you got to know. A log of base b, argument a, is equivalent to what?
The natural log.
Get it backwards. What's high stays high.
Oh,
Yeah, what's
I
high
have it.
stays high, what's low stays low.
I have it written down as natural log of 15 over natural log of 7.
Natural log of a over natural log of b. So the 15 is high, it stays high. What? When I'm talking about math or just whatever the hell we want to talk about. Because that seems to be the case with this class every single day. Now, a few of us in here, we're still doing that crap. You've had a long day, kids, so have I. Is that something you can punch buttons on and calculate? Yeah, let's go, get to that. Let's see, I don't have that on a shortcut, do I? Put a shortcut over there. No, the reason that ACT didn't go so well for a lot of y'all is because of the behavior you exhibit in class. That's the honest to God truth. You sit there in some other world. Like, I honestly wish I didn't give you guys Khan Academy as an option. But you sit there in some other world doing nothing. Like, you won't even type natural log of 15 over natural log of 7 in a calculator because you think you'll know how to do it on a test, and you won't because you haven't ever yet so far. How do you learn? By repetition, by seeing, by doing, by hearing. And I know you're not listening to me, and half of you aren't even looking. You're not doing it. You're not, there's no way you're going to learn with how you're doing. And I get that algebra 2 is rough, but it's not that rough. If this was an actual, that book that I gave you, take home this title probably, it would say Introductory Algebra. That's what it would say. It is Introductory Algebra. Anyways, we round this to what decimal? Not the fourth, so 1.3197. Because there's a 6 after that 6. Now, I'm going to do example B 2 different ways. You can do any problem this other way too, but we'll start off by doing the way we're familiar with, the same exact way we did example A. We want to use still that log is bay, but I've talked about this in class. The deal is that the base, the b to the e equals a part, the base part is what? Over here, this b to the e. Is there anything attached to it? A may as well be anything. It can equal anything, okay? So when I look at that 4 times e to the negative 3/10 of x minus 7 equals 13, I just got to decide to myself, is it isolated? No. It wants to be alone. It hates everything else in this world. So how do you make that thing alone? Adding 7 to both sides is a good strategy. If you were to add 7 to both sides, what would be on the left-hand side? Sorry, right-hand side. 20. You add 13 and 7, you get 20. Is the base of E still, is it isolated? Nick, what are you going to divide out? Nick, I'm asking you a sixth grade question, son. What do you got to divide out to isolate E? You have got to zone in. What do you got to divide out, kids? I'm not trying to be mean, but you're not here. Like, I realize you got a lot of crap going on in that head. Every one of us does. But a lot of us like to compound and compound and compound. E to the negative 3/10 of x is a 5. Now we're going to convert that into a logarithm. Tyler, what's that logarithm's base going to be? E. Right. Log of base E. Kiana, what's its argument going to be? 5, that's correct too. And I guess let's go with Nolan. What's it have to equal? What? Yeah, the only thing left, negative 3/10 of x. You want to know how we rewrite log base E? ln, natural log, right? What are we going to divide out with that x? Negative 3/10. I'll put it over negative 3/10. That's some x value. And then I go to a calculator, I type it in, and I round it. How many decimal places? 4. There is an ln key. That 7 gets rounded up to a what? 8, so negative 5.3648. Now, I said I'd do this one a different way too, because you need to see this alternate technique. I'm going to make it quick. Huh?
The way you did this one's easier than the way you did the question.
Well, that's because this one, our calculator has a natural log button. This one up here, the calculator does not. And I'll just make up something else. It doesn't have to be anything that's in your notes. Here's an alternate technique. It works for solving exponential equations. I don't care how you do it. It's called ln both sides, or lning, I guess we'll say, both sides. All right, so let me give me a constant. Give me a number, 1 through 10. 5. All right, 5, parentheses. This is going to be our base, something we raise up. So let me give me a base number. 7's fine. Rooftop, exponent. It doesn't have to be something simple. Make it something like 2x minus 5 or 3 or 6x minus 5, whatever. Make it something.
9x minus 4.
9x minus 4 is fine. Oh, do you want to add or subtract anything? Plus 8, sure. We want to set it equal to 13. Too simple. Because that's going to create a 1 when you divide out by 5. 29. What'd you say? 97?
Yeah.
Oh, 97. Make this thing ugly as crap. Now, there's a technique called lning both sides, but the technique still requires we still have to isolate the base. Apparently, I'm yelling at you. Base always has to be isolated. No matter what you do in exponential equations, you've got to isolate bases. What's up, Emily? Yeah. Didn't miss anything today.
Yeah.
Can you go to a printer and print it off? It's on the classroom. If not, come back during direct studies, okay? Anyways, let's go through the steps isolating that base. What you can do with your 8. Subtract it. That's going to give you what? 5 times 7 raised to 9x minus 4 equals to 91. Is the base alone? By the way, what is the base?
7.
7, right? Because bases have exponents. Why are you looking at me funny? It's 7 minus 8 is not 91. You told me 91. 89. Anyways, divide out what? 5. I do not encourage you to go to a calculator on stuff like this. I suggest you just write it as 89 over 5. Don't round it. Don't get a calculator, and if it gives you a decimal, round the decimal. Just leave it as a fraction. There's no point even touching the calculator, to be honest with you. Bases alone, right? Now we're going to just call a technique called ln both sides. Yeah. This reads 5 times, right? Opposite of multiplication is division. Get rid of it. Divide it out. All right, we're going to ln both sides. So left is going to become the natural log of 7 raised to the 9x minus 4. Right's going to become the natural log of 89/5. Now this is a fairly complex example, so don't think like this is harder than it was before. There's a lot of stuff going on in this example. You had a rule or a property the other day in your notes. It may have been written like this, but anyways, a log argument A with an exponent of R. Where's the R go? It goes in front. R logs of N. So that natural log of 7 has an exponent, doesn't it? It's 9x minus 4. Where do we want to move it? In front. So the same exact property of this thing. Move it up front. If it's 2 or more, you should wrap. You know, up top it was pretty clear it was by itself. When you move it down on the same script level, you need to wrap it to make sure you keep it together. I know you're a little intimidated by this whole natural log stuff, but big deal. You have 9x minus 4 times the natural log of 7. How do you counteract multiplication? Division. Divide that ln 7 out. So I have 9x minus 4 equals the natural log of 89 over 5 divided by the natural log of 7. What are we going to add to both sides? 4. You all right, girls?
Yeah.
Last step, we divide out 9. Well, anyways, throw the whole blessed thing over 9. If you take a standardized test, they do like to be a little tricky on things like this. Like that natural log 89 over 5. How do you export division inside of another? Subtraction. Like, see, a person who creates a standardized test, not necessarily ACT, but EOC in here, is probably write the natural log of 89 minus the natural log of 5. That's how they break it apart. It'd still be over the natural log of 7. Huh? No, there's no rule for that. This 9 down low is division. Division happens in a denominator, doesn't it? They'd move it right here. And this 4 over 9 would be written off the side by itself as 4 over 9. That's probably how it'd be presented on EOC. I guess it kind of confuses you. You know, odds are half your students aren't going to be able to get that far, much less rewrite to the next step, so I'm not sure why I do it. If you get this far with me, you're good. But, you know, be careful plugging this stuff out there. I wouldn't dare attempt to type that all in at once. You probably shouldn't either. Like, get the step by step. Natural log of 89 over 5, that's divided by the natural log of 7. What do you got to add to it? Gotta add 4. After you add 4, what do you gotta do? Divide by 9, you know. I break that into 3 good steps and done with it. About 0.6088. Now, the natural log technique is actually, this was a bad example to show you how easy it was, so I'm gonna do one more with it, if I got time. I'll show you how good it is on some things. This thing right here, 7x equals 15, 7x equals 15. You natural log both sides. This thing has 2 more steps, and it's done. Where's the x go? It goes in front. X natural logs of 7 equal to the natural log of 15. And what do you divide by? That same thing we had before? It better be. And it's a lot easier mentally. I know the conversion from exponent to a logarithm is really, it can be a little bit draining, especially in the logarithms. Adding both sides is actually easier mentally. And you end up using change of base anyways, don't you? I mean, it kind of saves you that step anyways. It's actually implementing change of base right off the get-go. But you do it homework however you want to do it. I don't care. You got to convert to a logarithm and then use change of base, or you can run on both sides from the get-go. I don't care. But pick one, go with it. That's your instruction, kids. You got 30 some odd minutes left in here. You want to work on your homework, you can. You want to work on Khan Academy, you can. You need to be doing math, though. The hole puncher, get it? Stinking hole puncher.